That makes sense. I did it the same. So it would be 28% then.
So I'm going to be up here catching up to you.
For C, I got the mean was 45.172. Let's see if our numbers match up. I'm going to restart that. Add that one time. Sometimes I fat finger it, so it might be right.
I had 38.53.
Yeah, you're right. Sorry. You were right.
You might have just left off the 2 at the end.
I had 38.53.
I'll have to catch up. I screwed up that data.
All right, guys. So what I just did, I went to stat, calc, one of our stats, and then did it on L3. And then we just look at the sum. That's the sum of the third column. That's where I'm going to get my mean from, right? So if you want to do it that way, especially if you give you a longer list of data, you want the calculator to chew it all up, and then you can just copy it down. So let me switch over to the worksheet. Okay. Things work so much better when you turn it on. All right. So that's where we are right now. Does that look the same as yours? Never know. Okay, good. All right. So then, for it to be a valid probability distribution, two things always. They all have to be between 0 and 1. And they all have to add up to be 1. Which kind of makes sense. It's kind of silly little things. We all kind of know them, but I still need you to say them when I ask you that question. All right, so verify this is valid. Don't just say yes. Say those two things. And actually make sure that's true. I might throw a curveball at you. You never know. Okay, this is kind of interesting. So the whole idea of at least 1 equaling 1 minus none has got nothing to do with at least 1 and none. That's not a special case. It's just any time I ask you the probability of something and the opposite has less stuff associated with it, I'm going to do the freaking opposite. So if I want to know what the probability that there are 25 or more, I could just do 1 minus the probability of 21. That's the only one I left out. And why does that work? Because they all add up to 1. So 1 minus a part of it must equal the other part of it. Now, is this such a big deal? If you added 0.21 and 0.25, who cares? But this becomes very important later on. So I want to make a big deal of it right now. So the probability greater than or equal to 25 is 1 minus the probability that they're 21. It's the only one I left out. And that's 1 minus 0.07, so I get 0.93. How are we doing so far? Pretty good? Pretty good? So if I would have said what's probably that they're less than 100, they think they'll be less than 100 by the time they retire. Hopefully that was some of the younger kids that don't really understand age. 1 minus 0.02, 98. So if you add all these, of course, you'll get 98%. So it's just a quick way to do a probability problem. If the opposite situation has less stuff, I'm going to do the opposite, do 1 minus that. It's just quicker. All right, so now I've already got the mean. There's my mean, 47.17. Kind of makes sense. I mean, what shape is this distribution sort of? What can anybody tell me something about this distribution? It's not really quite bell-shaped because there's a middle sort of here, and then there's another middle here, right? In a way, there's another hump. So it's like bi or trimodal, right? Is that cool? And it may be a little skewed in one direction or another, but not by much. So the mean being almost sort of in the middle, not really in the exact middle, but it kind of makes sense that that's what the mean is. It's not going to be towards one end or the other. It's going to be somewhere in the middle because it's semi-symmetric, not really. All right, that's enough of that. The variance. So now I just need this guy. I'm going to place him here. And I'm not picking on anybody, but this actually happens a lot. Happened to at least one person that I saw. Very often, for some reason, people forget to square that poor little mean. And that's not very fair. All this stuff is squared. So I got to square the mean too to make it fair. So the variance, whatever the hell that is, who's got that for me?
338.3611. I don't know how much you want us to round.
That's good. Basically, in your calculator, don't round at all until you get to the standard deviation, and then you round it.
To the third.
I like it, at least. I like it. See, now, you made the mistake once, you're not going to make it again. And so, if you do take, how do I get from here to the standard deviation?
Square root.
Square root?
18.
395? 5? Now, before I get too far, let me just show you, before I answer the rest of these, let me show you the ultimate shortcut, right? And you're like, you math people, my God. Let's do all this work. So, hopefully you understand. I'm about to show you the calculator will just give me these numbers really quickly. So that is not the way I want you to do it. That's the calculator doing it and getting credit and making good grades. This is you doing it, and then I'm going to show you how to check it. So, and before I get there, no, I don't have a VCR. Go away. It's just not enough options here. All right. All right. Good Lord. Yes. Cool. So here's the beautiful thing. So remind me, how many variables do I have in this problem? No, that's values. I have that many values.
200.
I have that many kids. How many variables? How many questions did I ask the kids? Each one of them asked one. So how many variables do I have? One. I have one variable that has values of 21, 25, 40. You guys with me? You understand? The P of X is still a part of the variable. It's still part of the data. There's just one variable. So I should be able to tell the calculator to do one var stats somehow. But tell me, why is L1 not enough to be the true data? I mean, those are the data points in a way, but why is it not enough? If I said that's my data, then I have 121, 125. So where's my true whole picture of my data?
When you see how much you have of that.
And which list tells me that? So L1 combined with L2, that together tells me my true data. I would have 7 21s and 21 25s and 25 40s if I talk to 100 kids. I talked to 200, so how many 21s did I have? 14. You guys with me? So together, L1 and L2 tell me what my one variable outputs were. Let me let that soak in. And the reason I'm making a big deal out of that is I can do one var stats. I can't do two because I only got one freaking variable. But I got to tell the calculator one var stats L1, comma L2. I got to give the calculator the whole picture. So if you do one var stats, get out of here. Oh, get out of here. Stat, calc, one var stats. L1, I can't remember, maybe this is the first time we used our comma. That's why I have punctuation in the calculator. Comma, L2. Do those numbers look familiar? Above the 7. Yeah. Isn't that nice? Isn't that nice? And mean old Mr. Waller, he won't let you just copy this shit down. But this is beautiful to know this exists because you can check yourself very quickly. And what do you think this means? It's interesting. Does this really represent the number of kids? What does this really represent then? This represents the sum of the probabilities. So if this was 1.1, you put something in wrong. Because it can't add it to be 110%. So that it has to be 1 when you're doing this XP of X stuff. When you do it in the calculator, it's got to be a 1 there for it to make sense. Or at least close, 0.997 or something, if they rounded. Does that make sense? So that's a really quick thing to check to make sure that you put everything in correctly. It's got to be very close to 1. All right, and so that's nice. It's good to know. All right, so let's go back and finish out the worksheet. Any questions on that while I have it up here? Is that decent? You guys, you don't have to even know how to get there. I'm not going to make you use a calculator, but it's really good to check your work. All right, so this sounds very familiar, and I think when we first did this kind of a problem I told you, I'm going to keep asking that same kind of problem over and over as we learn new ways of getting data. So here we got a new way to get data. I'm going to ask this problem again. So in the middle goes the mean. That's crazy. If I go up 1 standard deviation, where do I end up? 65.85. And then we go down 1.
28.700.
Blah, blah, blah. Okay. So which ones of my data points are actually in there? Is 25 in there? No. 40? Yes, 40's in there. 60? Yes, 60's in there. 65? Yes, 65's in there. And then 100, of course, those 4 kids, I don't know. Work until they're 100. I don't know about that. George Burns did, almost. So now you can't just do 1, 2, 3 out of 6 data points because there's not just 6 data points. So if I want percentages, I just go, okay, these are the ones I'm talking about, and these are their percentages. So just add up the percentages to get the total percentage of what you caught. I caught 25% of the data that I caught was 40. So 25% plus 16% plus 29%. What do you get?
70.
70%. So 70% of the kids said an age that was within 1 standard deviation of the average age that was given. How are we doing so far? Is that? These are the exact types of questions I would ask you on this problem, by the way. That's why this worksheet's very important. How many kids believe they will retire before age 50? Well, what percentage believe they'll retire before age 50? Yeah, if you add up 46 and 70 and 50, so 53% of what?
200.
So 53% of 200 is? 106. You get 50% of 50 or something. Yeah, so you're trying to think ahead. Maybe double what you would normally get. 53% of 100 is 53, so the 200 would be twice 53. So 106 kids think they'll retire before age 50. You never know. Might be true. All right. Cool, man. Any questions on that? You guys are all excited because you know what I'm about to say. There's no questions. That's plenty for today. Okay. Yeah. I'm going to give you guys the answer key for the practice quiz Thursday. The quiz has been moved to Tuesday. Remember? The double quiz. It just is twice as big, twice as much as a normal quiz.
That was like 2 quizzes at 2 different chapters.
No.